All right, let's take a look at page 261. So we're going to wrap up 4.4 today, and we're going to start 4.5. Today's just going to be kind of a reiteration of these different properties of rational functions that we've been discussing. And then we're going to take a look at our final characteristic for rational graphs, which are going to be horizontal asymptotes. And those can be a little tricky depending on what the equation kind of looks like. So we'll get there a little bit later today. On Friday, though, I believe we finished filling out this chart on 260. Does that sound about right? Probably? Okay. So it should be completed in your notes. I know it's not completed up here, but I want you to just take a second, take a look at the different values that we filled out in the columns, and can we make some generalizations about a certain characteristic that might be on the graph and how that's related to the equation. Looking at this table, it looks like we were looking at factors, restricted values, holes, vertical asymptotes, things like that. Can we make some generalizations? We're going to write those down on the next page. Basically, did we notice any patterns within this table? Good, Grace. Where? The restricted values. Okay, so restricted values result in vertical asymptotes or holes. I like it. So restricted values are numbers that make the bottom of a fraction 0, okay, the denominator. And if we can figure out where that might happen, we either have a vertical asymptote or a hole graphically. How can we narrow it down to whether a certain number represents a vertical asymptote or a certain number represents a hole? Yeah?
Whether it's 0 over 0 or a number over 0.
All right, 0 over 0 or a number over 0. What's the difference between the two? All right, one was a hole, one was a vertical asymptote. Can we label which one's which? If we plug in a number, yeah. 0 okay. There we go, perfect. So if we plug in a number and we get 0 over 0, we can basically relate that to the equation's factors. Okay, if we were to do some technique, factoring technique on top and bottom. If we plug in a number up top and bottom and it makes it 0, that means we have a factor up top and bottom. Which means if we're dividing and those factors are exactly the same, we can cancel those out. So for holes, we have canceling factors. For a vertical asymptote, though, notice how if a number makes the bottom 0, we have a certain factor in the bottom, but that same factor does not show up top, because if we were to plug in a number, we wouldn't get 0. So in this case, we have a leftover, okay, non-canceling, a leftover factor in the denominator. Okay, I think those are good. Those are the 3 big things I want us to get from that table from Friday. Now, our current table on 261, we're going to take a look at this characteristic of a hole a little bit more closely, because graphically we know a hole is where 2 sides of a graph meet at an open circle. Okay, that was the definition we used in a previous section. So if we have 2 sides meeting at an open circle, that means the 2 sides are meeting at a particular height, aka a y value. So not only does a hole have an x location, okay, on an x-axis, but it also should have a y location. So let's see if we can figure out where that y location is. These four examples are the same ones that we had on page 260. And in the first column here, they want us to rewrite it in factored form. So can you do me a favor and just copy down the factors that were on page 260, since they're the same. All right, these were the same factors that we had from Friday. So based off these factors, can we identify a spot where we have a hole? Okay, I know up top it says point discontinuity, but that kind of just means the same vocabulary term as a hole. Can we find an x value? Go, Caitlin? 3, there we go. All right, so x minus 3 factors cancel, so the solution from those factors is the location of our hole. Looks good. Now they want us to find the value of the simplified form of the function at this x spot where we have a hole. So our simplified form is basically the factors that are left over, the ones that did not cancel. So we'll have a 2x plus 1 and an x plus 2. Okay, we canceled out the x minus 3's. So let's see what would happen if we took this location of a hole, okay, the x value of 3, and plugged it in to the simplified form. We know if we plugged it into the original, we'd get 0 over 0, because that signifies a hole. But what if we plug it into the simplified form? We would get 7 over 5. Okay, if we plugged in 3. So let's see what this number, 7 over 5, represents graphically. Okay, on page 259, I'm going to show it up here, we had this graph of f of x. Okay, the same equation that we were just analyzing. And notice how at the x location of 3 we have the hole, but in terms of 7/5, it seems like that would fit as a y value. And notice how they specifically state that kind of at the top. So not only can we find the x location of a hole, okay, based off those canceling factors, but if we wanted to find the y location, we simply just have to take the x value and plug it into the simplified form. Okay, not the original though, because that gives us 0 over 0. Okay, the simplified form. So based off the graph, it looks like we have 7/5 as well. So let's see if this kind of works out for some of the other graphs. Okay, visually, for g of x, they tell us the y value of the hole is 1/2. For h of x, they tell us the y value is 1. And for p of x, the y value of the hole is -1. Okay, so we're anticipating what our result should be. Let's see if we can actually get that based off the equation. So for the next one, g of x, can we find the x location of the hole? Okay, Caitlin? -3. Okay, so the factors of x plus 3 cancel. We're going to take the leftover factors, x plus 1 over x minus 1, and we're going to plug in -3. So that would give us -2 over -4. But notice how if we were to simplify that, that would just be a half, like the graph was telling us. So it seems like we analyze that function correctly. Okay. What about h of x? Can we find a location of a hole? Caitlin, you're on a roll. -2. Okay, so the factors of x plus 2 canceled. What's our leftover fraction? We definitely have an x plus 3 left on the bottom, but the x plus 2 canceled up top, yeah? 1. Okay, it's a placeholder of 1. You might think it's 0 because it goes away, okay, but it's a placeholder of 1 because technically anything divided by itself is 1 after all. So that's kind of what's left up top. So if we take this x value of -2 and plug it in, we'll have 1 over 1, okay, which matches what we have based off the graph. So for our last one, looking at it, the x plus 2's would cancel out. So -2 is the location of our hole. Our leftover factors, 2x plus 3 over x plus 3. And if we plug in -2, we'll get -1 over 1, which is -1. So it looks like this characteristic is solid, okay, for every single function that we have. So just like how we generalized some patterns from the table from Friday, maybe we can generalize a pattern from the table that we just filled out. Okay, so we can say the y value of a hole is found by what? Can we summarize it? How can we find the y value of a hole? From an equation. We use the graph to kind of check our work, but how did we find it from an equation? Can you describe it? What do you think, Noah? Okay, by plugging in the x value of the hole into the non-canceling, okay, leftover, if you will, non-canceling factors. I like it. Okay, so I know we've talked about a lot of different properties of these rational functions. We have x-intercepts, y-intercepts, holes. We can do x values and y values of holes, and vertical asymptotes. Okay, I think that kind of brings us up to 5 in terms of characteristics. So what we're going to do in our 4.5 is just kind of review or reiterate those 5 different characteristics, and we're going to add on our 6th and final one, okay, which is going to be those horizontal asymptotes. So take a look at page 265. We're going to kind of bring everything together in this example. We have a function at the top in standard form, and then they're also nice to us and they give us the factored form as well, so we don't have to worry about using any factoring technique. Before we start to fill out any of the boxes at the top, let's see if we can go ahead and just jot down what different characteristics are, or how they're found in terms of these functions. So if I were to ask you, or tell you rather, that the denominator does not cancel out, okay, a factor in the denominator does not cancel out, what do we have graphically at that spot? A factor is left over in the denominator. Yeah? Horizontal? We're going to get there eventually. Okay, it's a vertical one. Okay, denominator meaning bottom. Okay, makes the bottom 0. It's left over there. What about if we had a factor in the numerator that didn't cancel out? So in our first example, this would be like a number over 0. Okay, we'd have a factor that didn't cancel out. In this case, we have 0 over a number. Yeah? It is an x-intercept. What if we had a factor in the numerator and denominator that cancels out? AKA 0, 0, yeah? That's a whole. Okay. And then what if we were to take the quotient, aka division, of the constant term of the top and the bottom? What would that give us graphically? Yeah? That's a y-intercept. All right, good. Okay, so those are the big ones that we've discussed so far. X-intercepts, y-intercepts, wholes, vertical asymptotes. So based off of these descriptions of how the characteristic relates to the equation, let's see if we can find those based off the example at the top. Now I know we have a graph, which means we should be able to at least check our work, but let's see if the answers we get actually match what the graph is telling us. So for these canceling factors in the denominator, okay, the ones that would be left over, take a look at the factors. Which bottom factor does not cancel out? Go ahead, Caitlin. The x plus 2. Okay, so we can see how there's an x minus 1 up top, or x plus 1 rather, up top and bottom. So those cancel. Left over is x plus 2. If we were to solve it, okay, find that factor's solution, we would get negative 2. So based off of what we said at the bottom, this negative 2 should be a vertical asymptote. And visually, that seems to check out. Okay, x value negative 2. If we take a look at the non-canceling factor of the top, okay, negative 2x plus 3, let's find that solution. You can subtract the 3 and divide negative 2. So that'd become 1.5. Based off of what we said at the bottom, this value should be an x-intercept. And graphically, seems like we have that x-intercept at 1.5. So that's checking out. If we take a look at the canceling factors, okay, that would be the x plus 1s. If we find that solution, aka negative 1, we said at the bottom that should be a location, an x location of a whole. And at negative 1, notice how that's there. Now I know it's not a part of the actual question, but let's see if we can find the y value of the whole. Graphically, it should be at 5, because we can see that. But let's get the same result from the actual function itself. So what we said on the previous page was if we took a look at the leftover factors, the one up top and on the bottom, we can plug the x location, okay, negative 1, into those to get the y value of the whole. So if I plug in negative 1, I'll get 2 plus 3 over 1, which is 5. Okay, so we can figure out x locations, but also y locations of those wholes. All right, the last one, quotient of the constant terms. So looking at the standard form this time, not the factors. Constant term of the top is 3, constant term of the bottom is 2. We said it below that this value should represent a y-intercept, and graphically that seems to check out. Okay, so that's a very good summary of basically all these different characteristics that we've discussed so far with these rational functions. Okay, vertical asymptotes, x-intercepts, wholes, y-intercepts. Okay, we're going to add one more to the list today. We ready? You don't really have a choice, right? Okay. So our last characteristic is horizontal asymptotes. So we already talked about vertical. Now we're going to move on to horizontal. And what's a little bit tricky with these is there isn't really one quick cut way to figure out where a horizontal asymptote is located. We have to kind of take multiple things into consideration depending on the case. So this is what can be, of all the characteristics, this one might be a little bit more, not difficult, but demanding, I guess, for us to figure out. Not that it's hard, it just says we have to take multiple things into consideration. So looking at these first two examples, okay, of equations and graphs, I want us to take a look at the degree, okay, the highest power of the top part of our fraction and the bottom part of our fraction. If we take a look at f of x, what's the degree of the top? The highest powered from the top? 1, because it's linear. And what about the degree of the bottom? 2, because it's quadratic. Okay, same thing's going on for the second example. Okay, 1 over 2. So for both of these, I'm going to kind of write off to the side here. The top degree, I'm just going to abbreviate T, is less than the bottom degree. Okay, top is less than bottom. What do you notice about the horizontal asymptote for both of these graphs? Can we list where it's located? Yeah? On the x-axis, which has a y value of 0. Okay? So for both of these examples, because the top degree is less than the bottom, it seems like, okay, based off of a pattern, I know we only have 2, but if we had a little bit more, maybe that would work as well, that the horizontal asymptote is always going to be at 0. Okay? Can you think about why that is? I might get into some calculus understanding. What would happen? Yeah.
Is the numerator the degree of x squared, like the leading coefficient? That would be if there was an x squared is 0 in this case, and 0 divided by 1 is 0.
So that you're actually going to lead us into our third case. Okay, you can think about it that way. Okay. Horizontal asymptotes is kind of telling us about the end behavior of a graph. Okay, does it go up, does it go down, or does it level off? And if it levels off, we know we have that horizontal asymptote. So if we're looking at the ends, that means the x value is getting either really, really big, like positive infinity, or really, really small, like negative infinity. What would happen if I plugged in a really big number, bless you, into the top versus a really, really big number into the bottom? If you plug in a really, really big number into the top and you subtract 3, isn't it still a really, really big number? Do you notice how the subtraction of 3 is basically insignificant? Does that kind of make sense? Okay, so the top part is really acting just as an x because the minus 3 doesn't even matter if you plug in a really, really big number. If you plug in a really, really big number into the bottom and then square it, isn't that even massively larger? So it seems like the subtraction of a really big number, because that number is even smaller than after you square it, and then minus 6, those are insignificant. So the bottom is really acting like an x squared. Okay, so if we think about simplifying this, this basically is 1 over x. And what is 1 over a really, really big number? What's that really close to? Like 1 over a million. Isn't that basically 0? Isn't that what we're approaching, right? It's a horizontal asymptote. This is the reasoning behind it. Okay, in here we're just basically going to talk about the patterns, but the reasoning is kind of a calculus understanding. Okay, thinking about what would happen if you plugged in different values. Okay, but for now, if we can just remember the top is less than the bottom, that means a y-intercept at 0. That's what I'm looking for. Okay, but this is why it boils down to that, because you have something really, really big on the bottom, but not the top, which basically approaches 0 for really large numbers. Okay, let's take a look at the 2 at the bottom. Okay, what about the degree of the top versus the degree of the bottom for these two? The degree of the top, good, Maggie?
The degree of the top is 1 larger than the degree of the bottom.
It's bigger. Okay, it could be 1 larger, it could be 2 larger. Okay, but it's bigger. Notice how degree of 2 up top versus degree of 1 on the bottom. Where's the horizontal asymptote in these graphs? Where is that horizontal dotted line? What do you think, Maggie? there's no horizontal asymptote, okay, but we do have something else interesting going on in these graphs. Instead of a horizontal dotted line, notice how it's slanted, diagonal, okay? It has a slope to it, a little bit different, okay? So when the degree of the top is bigger than the degree of the bottom, we're not going to have a horizontal asymptote. It's going to be kind of diagonal or slanted. So no horizontal, but we'll say a slant one. Have we seen those before? Slanted ones? Okay. We're saying yes like we didn't like them. We didn't. Maybe we will this year. Okay. All right. So we've talked about two options. If the degree of the top is less than the bottom, if the degree of the top is bigger than the bottom, what's our third case? If they're the same. Okay, so let's see what happens in this one. Take a look at the next page. These two examples, notice how degree of top and the bottom match. Okay, so top degree equals bottom degree. Where is the horizontal asymptote in these pictures? Maybe we'll say where it is for each one individually. Where's the horizontal asymptote in our first graph? Looks like 2. Where's the horizontal asymptote in the second graph? -1. Okay, so unlike the previous two cases, okay, where it was either always 0 or always slant, in this case we might have different outcomes. Okay, depending on what this is just telling us that the degrees are the same, but notice how the outcomes are different. Where do you think this 2 and -1 are coming from? Yeah? We're dividing the leading coefficients. So the 2 divided by the 1, that's going to give us the 2. And then the -2 divided by +2 is giving us the -1. Okay, so all three of these cases are going to help us find a horizontal or slant asymptote in some capacity. It all boils down to the relationship, though, between the degrees of the top and the bottom. So we have these three outcomes, or these three possibilities I just want to kind of summarize at the bottom of the page. Okay, what if the top degree is less than the bottom? What if the top degree is more than the bottom? What if the top degree is equal to the bottom? All right, so for these three cases, can we make a rule, if you will, as to where the horizontal asymptote is located? If the top degree is less than the bottom. Sometimes you might hear me refer to this as bottom heavy, meaning the bottom has a higher degree. That's a little easier than saying the top degree is less than the bottom. Just say bottom heavy. What do we think? If you have something small divided by something large, you're basically, yeah? You're on the x-axis. You're close to 0, right? Like 1 divided by 1,000,000. Something small divided by something large. So horizontal asymptote at y equals 0. Okay, the x-axis. This is always, okay, if the top degree is less than the bottom. If we flip it, though, if the top degree is more than the bottom, sometimes you might hear me refer to this as top heavy. Kind of a quicker phrase. What happens with our horizontal asymptote in this case? Yeah? There isn't one. So there's no horizontal asymptote, but what do we actually have? A slant. Okay, so there's some other dotted line that we approach. It's just not perfectly horizontal. It happens to be diagonal. There's some slope to it. What if the degrees are the same? So you might hear me call this equally heavy. Where's our horizontal asymptote? We can't really say it's always 0, it's always 2, it's always -1. Can we make it a little bit more general though? It might not be always a number, but we can say it's always something. How did we get -1? Yeah?
Is it the top leading coefficient divided by the bottom?
Okay, perfect. So horizontal asymptote at the division of the leading coefficients. Okay, so the top divided by the bottom. It's kind of similar to how we did y-intercepts, where we had to do the constant term of the top divided by the constant term of the bottom, but now we're just looking at leading coefficients. This is only if, though, the top degree and the bottom are exactly the same degree. Okay, you only do that if they're the same. If they're not, you have these other two cases. So this is why horizontal asymptotes can be a little bit more tricky, because we have 3 cases that we have to consider. It's not just as clear-cut as a whole or a vertical asymptote is. Okay, but I think we can handle these 3 different rules. Do those make sense graphically? Okay. We're going to spend some time though talking about slant asymptotes, like how we can find them based off an equation. So that's what we're going to kind of end today with on the next page. So these 2 examples, we're going to take a look at graphically where the slant asymptote is, but also how we can get the slant asymptote from the equation. Okay, what if we didn't actually have a graph available to us? Since we do though, can we maybe think about the equation of that slanted line? Can we pick apart different characteristics that can help us write the equation of a line? Yeah?
Slope is 1.
Slope is 1. Okay, so if you pick some points, do rise over run. Alright, slope is 1. Yeah?
The y-intercept is 4.
Y-intercept is 4. Alright, so plus 4. So here's the equation of our slanted diagonal asymptote. Sometimes they're called oblique asymptotes. Kind of like on the human body, if you have obliques, I definitely don't, they kind of go diagonally. Okay, oblique asymptotes. Let's see if we can get the same result based off the equation. Okay, so here's the equation on the left-hand side. And in order for us to figure out or find the equation of the slanted asymptote, we're going to go back to synthetic division, our favorite from Unit 2, okay, which we did a lot back then, so I think this is really going to be kind of simple for us. So let's go ahead and think about what our outside kind of box number would be, and then what the numbers are for the rest of division. Can we think about what number we need on the outside? If only one number can go there? What do you think, Noah?
In this case, it's probably 1, right?
Where'd the 1 come from? Yeah.
The denominator.
The denominator. Okay. That's your divisor. Yeah?
What if on the top we have a power of 3, or like a degree of 3, and then on the bottom a degree of 2? Which one would you pick?
Now if it's a quadratic on the bottom, there's probably 2 numbers.
Yeah.
So you'd have to do synthetic division twice, 1 for each. We're not going to get into that. Okay, we're going to keep it simple with linears, but that's a good question. Okay. What about the numbers in here? 1, 3, 2. Okay, the coefficients from the numerator, the polynomial up top. Okay, so if we go through synthetic division, we'll drop the 1, 1 times 1 is 1, 3 plus 1 is 4, 1 times 4, 4, 2 plus 4, 6. Can you find, or can you see the equation of the slant asymptote showing up somewhere within synthetic division? Where do you see a 1 and a 4? I see a 1, 4, and a 6. What's the 6 represent, though? That's the remainder, right? So it looks like in our synthetic division analysis, I don't really care what the remainder is. That just tells me if it's a factor or not, okay? But it looks like the quotient, okay, the stuff that goes in at the top, a whole amount, would be 1 and 4. So if you put the x's back into that, you'll have an x plus 4. Okay, the equation of your slant asymptote. Kind of interesting. Let's try the one at the bottom. Since we have a graph, can we anticipate where the slant asymptote should be? At least when we work it out by hand, using the equation. Can we find the equation of that line? Slope is up 1 over 2, so a half. Y-intercept, -1. Okay, so let's see if we can get the same result based off synthetic division. So here's our function. The number that makes the bottom 0 would be -1. And we'll have 1, -1, and 1 for our coefficients. All right, so synthetic division, drop the 1, go from there. If I ignore the remainder, that just tells me if it goes in evenly or not. Clearly it doesn't. The quotient would be x minus 2. But that doesn't really match the equation we found from the graph. So did we do something wrong? Did we not go far enough? Does synthetic division not work every time? Yeah?
So, like, the leading coefficient of a factor on the denominator starts
Yes?
with 2, so you gotta divide by 2.
Do we remember that little fact when we did synthetic division earlier this year? This is why. Okay, we didn't really focus a lot on it earlier, but now we will. Okay, because that coefficient in the bottom, okay, 2 in this case, must be divided by your quotient, because we'll get a 1/2 x and then a -1 if we do the individual divisions. So that's where it comes from. So if you weren't able to focus on that little synthetic division property earlier, bless you, we're going to have to get used to that now, because it can drastically change the location of your slant asymptote. Okay, we'll do more of that tomorrow. Are we okay so far? I should have checked earlier. Are we good?
Everybody's fine.
Yay! Okay.
I sneezed 3 times.
I heard, they were quiet, but I heard it.
Are we going to do long division ever?
No.
Yeah. That makes my life like 300%.